Okay, thanks. Thank you for your introduction. So today I will talk about our work on unifying approach to product constructions for quantitative temporal inference. So this is an overview of today's talk. And first I will illustrate what is a quantitative temporal verification and product constructions. So this is an example of quantitative temporal verifications. So let's say as a system or target program, we have a probabilistic program. And here this diagram represents operational semantics of probabilistic program, which is actually a Markov chain. And here this transition represents behavior, like executions of the program. And when it's terminated, it basically leads to this target states. And as a semantics of this probabilistic program, we consider traces or like probabilities of traces. Therefore, the semantics of program is basically a sub-distributions over the traces. And now the specification for such a type of program is given by a DFA, and DFA, deterministic finite automata. And this automata describes what kind of traces is acceptable or like desirable for the program. And given this system and specification, we would like to compute, for example, the probability of accepting traces. And formally, this is given as follows. So this Q is we called inference query, which defines the verification problem, which defines the temporal verification problem. And here, nu is basically behavior of the program. And this L is the specification given by the DFA. And basically, the problem asking to compute what is the probability of accepting traces over the program. And there are a couple of examples, including emptiness checking of accepting traces for more like a non-deterministic programs. And also, we can consider shortest accepting path, which is more like for weighted non-deterministic programs. And now a question might be, how can we actually solve such a temporal verification problem? And there are many ways to solve, but one well-known technique is so-called product constructions. The idea is actually indeed very simple. So it basically constructs the product of system or program and the specifications. And now the states of the product is basically just a pair of the states of the program and specifications. For the example I showed, we can show that actually the reachability probability to the specific target states on the product Markov chain is basically, it's precisely the same as the probability of accepting traces, which is the original quantitative temporal inference problem. Now, our aim of this talk is basically providing a unifying theory for such a product constructions. The first question would be, actually, how can we define such a product of a system and the specification in general? And our short answer is using distributive law. We will show it later. And the second question we will address is, what is the correctness of products in general? And our answer would be establishing the following equations. So this is the equations, and this left part basically describes the quantitative temporal inference problem. Here, this denotation x and y is basically the semantics or behavior of the system and a specification, respectively. And this inference query Q computes, defines the temporal verification problems. And on the other hand, this right-hand side basically corresponds to the semantics of the product or like a behavior of the product. And this equation establishes the correctness of the product construction, which means the solving product is equivalent to the solving original temporal verification problem. And our goal of this talk is first providing a uniform way to construct a product, and then we will showing their correctness by a simple sufficient condition, which we call a correctness criterion. So next, we move to the coalgebras semantics we use for our framework. So coalgebra is an abstract and generic representation for transition systems. And in this talk, we focus on coalgebra, which is basically a functions, and where f is an end functor. And in this talk, I couldn't tell the detail what is an end functor, but for the example we use, it's actually very simple. For instance, for the labeled Markov chains, it's basically just a functions, and this part represents the transition probabilities to the successor states, and this part corresponds to the label that assigns for each state. And similarly, we can model DFA as a coalgebra, and also we can represent their product Markov chain as a coalgebra as well. And also, there are many ways to define semantics of coalgebra, but in this talk, we define a semantics of coalgebra as a least fixed points of predicate transformers. And for instance, for the product Markov chain, the least fixed point of the predicate transformer indeed corresponds to the reachability probability to the target state. And with this formulation, we reformulate the target problem, which asks when the inference query Q preserves the least fixed point. This is our reformulated problem. Now, so this is first contribution. So we define a coalgebraic product construction by a so-called distributive law. The idea is we translate the transition type of system and specification, which is basically program and, for example, DFA, to the transition type of product. And formally, this translation should be a natural transformation from functors for system and specification to the functor for the product. And you may wonder why we require naturality here, but indeed, naturality is important to ensure the correctness of product in our main theorem. And together with this distributive law, and given two coalgebra, one is for system and one is for specifications, we can actually construct a coalgebraic product as follows. So the first, it takes just a Cartesian product of these two coalgebra. One is for system and one is for specifications. And then we combine with distributive law and we change the transition type to the type of product. And of course, this construction covers the previous example for the probabilistic program cases. And secondly, we will introduce our main theorem, which is about the correctness of coalgebraic product constructions. And before showing our main theorem, we recall that our predicate transformer are actually induced by so-called modalities. I couldn't tell the detail about modality, but basically modality is an algebra. And the idea is the modality determines the way to update the semantics in one step. For example, for the product Markov chain cases, the modality updates the probabilities of computes the expectations for the probability from successor states, which basically corresponds to the probability from the current states. And since the predicate transformers are induced by modalities, actually this modality essentially determines the semantics. Therefore, one observation here is that a given distributive law should work nicely with modalities to make the product construction correct. So this is our second contribution, which is actually our main theorem, which is so-called correctness criterion. The theorem says that the coalgebraic product is correct. That is, we have this equation. The left-hand side is basically the original temporal problem, and the right-hand side is the semantics of the product. And they are coincide if the following conditions are held. The first condition says the inference query Q preserves the least elements. The second condition asks that the query preserves joins of omega chains. And the last condition asks this diagram commute, which basically saying the computation of this part coincides with the computation of this part. And indeed, the proof is not too complicated, and it's actually in the proof we show this inference query Q preserves the clean iterations. In fact, the first case is for the base case, and the second condition is for the limit, and the third condition is for the one-step compositionality or like step cases. And indeed, it covers a variety of instances. For example, partial expectations or cost-bounded reachabilities or optimization with weighted programs. So lastly, I will recall some related work and also show some future works. So there are a couple of work on generic approaches to verifications based on coalgebra in a uniform way. And our novelty would be providing a generic product construction for temporal verifications and also its correctness criterions. And there are lines of work on coalgebras semantics for LTL. And compared to their approach, our framework is based on distributive laws and inference queries. And consequently, they assume that systems and specifications share the same effect. But in this work, we can actually combine different effects. But on the other hand, they can deal with omega regular properties, which are unfortunately beyond our framework scope. And also, there are work on symbolic product constructions, and there they propose product construction on program level in a symbolic way. And currently, our product construction is defined on the operational semantics level. Therefore, it's not compositional and it's not symbolic currently. And as a future work, we are actually very recently proposing a unifying approach for symbolic product constructions. And here we can actually construct product programs in a symbolic and compositional way. And also we are interested in studying when we cannot do product constructions. And indeed, in the paper, we conjecture that there are no coalgebras product Markov chains for Markov chains and non-deterministic finite automata. And very recently, indeed, we showed that there is no coalgebras product Markov chain for Markov chains and the non-deterministic finite automata. And also, it will be exciting if we can support continuous distributions. That's it. Thank you for your attention.
If you have questions, please come over to that mic or this mic here. Yep, okay.
Hello, Henning Urbart, VR Langen. I was wondering whether your approach could extend to product constructions of automata, like Büchi automata, for example.
Yeah, that's actually an interesting question, but we don't have answer yet. In a more, yeah, it's a bit tricky. For example, if you want to talk about probabilistic case, you need to define measures, and you need to take account of also quantitative feature of these kind of behavior, including, for example, reward, expectations of reward. And for currently, we don't have an answer for this, but it will be exciting if we can do this.
Okay, thank you.
Another question? Okay, yes, go ahead.
Hi, nice theory. One question, is there any gap between the theory and the implementation?
Sorry, could you repeat?
Is there any gap between the theory and the implementation? For example, based on this product construction, whether we can do some verification work based on existing tools or the one we may develop by self? Yeah.
So currently our product construction only defines on the operational semantics level. Therefore, it's actually hard to apply it's hard to develop algorithm on top of our framework currently. But our aim of this work is more like providing a way to how we prove the correctness of this approach, the product construction. But also in the as a future work, we would like to develop the product construction on the syntax level. Then we can construct a product as a program, and then we can literally run the algorithm on the symbolic level. But this remains a future work. So currently we don't have an implementation for this work.
Thanks.
Yeah.
Other questions? Okay, I have a question. I'm not clear on the kinds of applications you have in mind for this, but a problem that's particularly interesting to me is sampling, sampling solutions of certain constrained problems or things like that. Is this suitable for sampling? Does it give you any shortcuts to sampling?
I think so. I think so. Because then, based on our framework, we can show that actually sampling on the product is actually correct in order to solve the original temporal verification problem. So it's actually justify why doing sampling or like inference on the product is correct with respect to the original problem. And we want to establish what is a kind of generic way to show or a systematic way to prove this